Everybody, my name is Jay Gordon. Welcome to the Azure Cosmos DB Global User Group for July. Thank you for showing up and being part of this. We do this once a month, usually the first or second Tuesday, and we try to get together and feature members of our community, and we've got a really great one for you today that will come here and talk about all the benefits of using Azure Cosmos DB with your different applications. So please, this is an interactive session. If you can, leave comments, leave questions. We will try to get to them as we go through this. Session should be somewhere between 1 hour to an hour, 15 minutes. We're going to give Lenny, who is our guest today, plenty of time to go through his presentation. Before, we got a little bit of housekeeping to do, and I've got my member of the Reactor team, Askia. I'm trying here to say it properly.
That's it.
You're here and part of the Reactor team. You got a little something to show us and tell us about before we bring in our guests. So please, tell us what you got to do.
All right. Thank you. Well, hello, everyone. And thank you for joining us for today's session. Just a few housekeeping tips to go over before we get started. Like Jay said, my name is Askia, and I'm the facilities coordinator for the Redmond Reactor Space. We've got a code of conduct that we'd like to go over, so we'll jump right into that. Here at Microsoft, we seek to provide a respectful environment for both our audience and our presenters. We encourage engagement in the chat, but please be mindful of your commentary, remain professional and on topic. Useful links are going to be shared throughout the chat. So just to let you know, this session is going to be recorded. It will be available on our Microsoft YouTube channel within 24 to 48 hours after the event, which brings us to today's session. So I will now turn it over to our speakers.
Thank you very much. Appreciate it. And we'll see you at the bottom of the show to just do a little bit more housekeeping. Cool. So, as you can see, today is building event-driven microservices with the Azure Cosmos DB change feed, a really, really powerful part of Azure Cosmos DB. Excuse me. Still trying to figure out how to talk. And to help me do that today, I have our guest. It is Leonard Lobel. He is a prolific teacher of Azure Cosmos DB through different and various channels, like doing great presentations. I've taken courses that you've done. Hi, Lenny. Welcome.
Hi, Jay. Great to be here.
It is so nice to have you back. You've done these before with us. I'm always really thankful because the information that you can share with our community is tremendous. And once again, today you've come to us with something that I feel every single developer really needs to understand, especially in this world of building intelligent applications that need to scale, that need to be able to have fast updates. You have got some great information for us today, and I'm going to give you some space to do that presentation, but I just wanted everybody to kind of get a quick introduction to yourself. You just tell everybody what you're doing, what you do, and where you do it.
Hi, yeah, sure. So I am a Microsoft MVP, now renewed for the 12th consecutive year, and working very close with Cosmos DB since its early days of Document DB, close with the product team. Done lots of Pluralsight courses and other conferences and seminars and workshops, etc. As well as, of course, my life in the relational world of SQL Server, where I've written several books, and I do also lots of speaking and writing on our good old friend SQL Server.
Wonderful. I really appreciate all that you've done around teaching data modeling for our NoSQL and Azure Cosmos DB. It's really helped me. I'm not going to lie. When I first started on the Azure Cosmos DB team, one of the first things I did was that you had a Pluralsight course that focuses a lot about data modeling in Azure Cosmos DB. I love it. I recommend everybody.
We'll definitely touch on that at some point in this session.
Great. So, Lenny, I want you to bring up your.
Hopefully have fun doing it.
Have fun
in the process.
So I'm going to ask you to, and one of our viewers, Mike Porter, he says that your Pluralsight course got him through the DP420 certification. So I think that's really cool. You are a known quantity for good.
That's great. That's super gratifying. Great. It got me through the exam too.
Awesome. So I'm going to ask you to go ahead and set up your presentation. And Lenny's going to go ahead and because we've got some issues, we're going to have him just do the whole presentation at full screen. So you'll be able to see every single piece of his demo, his presentation. I know he's got a big demo set to present to us. So Lenny, I have got your presentation screen up. I'm going to go ahead. I'm going to go on mute, and I'm just going to let you rip through it. All right?
Well, thank you, Jay, and thank you all for joining. And I am really glad to be here to present this session. Yeah, it's a mouthful here, building event-driven microservices with the Azure Cosmos DB change feed. But break it down to the three components, which are the change feed, microservices, and event-driven, right? And those are the three main parts of what we'll be, talking about today. I don't want to spend really much, if any, time talking about myself, other than, like I said, I've been doing this for a long time, doing lots of speaking and writing. I'm also a Microsoft consultant with Ernst Young and Microsoft MVP and yada, yada, yada. Enough about me. Let's just jump in. There is a link here. I believe that Jay, you'll make this link available. But if you go to this link, it will take you to my OneDrive, where you can download a zip file of all the code and this PowerPoint presentation. And with that, let's talk about the objectives today. So this is a bit of actually an advanced session, but fear not if you're new to Cosmos DB. I imagine many of you are familiar, but many may not be. So we will, for the benefit of those that are like really new to Cosmos DB, at least discuss partitioning at a fundamental level, because it's really kind of difficult to get into any kind of serious conversation about Cosmos DB without discussing partitioning. And then we will look at the change feed, what it is, what it can do, and then put those two together to build microservices, in particular, event-driven microservices, by applying those concepts. Beg your pardon. So what we have in Cosmos DB is a container where we store JSON documents, and every time you store or update a document in the container, it gets emitted through that container's change feed. Right? Just think of it very much like a transactional log in a relational system, where if you just look at the log, you can see the sequence of events, right? You can replay that log, right? Because it's not just emitted through the change feed; it is also persisted in the change feed and could be replayed. And this opens up the door for lots of scenarios. Lots of scenarios can light up as a result. For instance, replication. If you have a need to replicate data from one container to another, the change feed is an obvious choice for monitoring the changes to keep the replicate in sync. And we'll talk about reasons why you might want to do that. Denormalization. So kind of Jay touched on that earlier, talking about my talk on data modeling. We're going to just touch on that topic in terms of denormalization to see that as another use case for microservices that are event-driven by the change feed. Obviously, any interesting event of interest that occurs when we are monitoring the change feed can be used to trigger notifications. Very often we'll want and need to materialize views, that is, as in real time, as data is ingested into the change feed, maintain a materialized view that is cheaper to query for clients than if the clients had to query against the raw voluminous data. And obviously, any data entering Cosmos DB can be shipped off further downstream to some other system, any kind of data movement requirement, pushing it off to maybe SQL Server, maybe cold storage, storing your hot data in Cosmos DB and leaving it there, not for the long term, but for the long term, pushing it off to, let's say, data lake or Azure Blob storage. All of these can be implemented as event-driven microservices, and you're going to see how. We're going to go through all of them. And the big benefit here is that they all consume the same single source, the same single event source, the change feed being emitted out of the container. There's no interdependencies between these microservices, which makes for a much simplified microservices architecture overall than one where you have interdependencies between microservices. You'll see how we can maintain isolation in terms of state for each of our microservices to keep track of where they are and have them function independently, all by consuming a single event source that is the change feed of a Cosmos DB container. So I promised we would review the fundamentals, and partitioning is just one of those fundamentals. So for those of you familiar with Cosmos DB, you know this already. For those of you less familiar, this is critical basic information. Yes, we have one container that we interact with for storing and retrieving JSON documents, but behind that container is a cluster, of course, a set of nodes, and that set of nodes has no upper limit. Technically, there's no upper limit to how many of these, let's say, call them servers, because each one has, like a server, a hard drive and storage. And therefore, this design gives you both unlimited storage and unlimited throughput, right? Because the more CPU you add, you have more throughput, as well as the more disks you add, the more storage you have, right? So as long as you partition your data appropriately so that you can maximize the potential of uniformly spreading your data across these clusters, it'll just grow and grow. So I call these servers, these black boxes servers. Technically, they are physical partitions, because each one of them internally is a unit of replication that Microsoft provides that's transparent to you, that guarantees your availability, even if you're not globally distributing your data. You still have redundancy. Each of these are replicated. But for the purposes of this discussion, just think of each one of these as just another server, just another box that is being maintained by someone else, right, by Microsoft. And we're not going to concern ourselves with these physical partitions. We'll drill into these three. We just know that when we store JSON documents into our container, they're going to land on any one of these physical partitions that are managed by Cosmos DB. So how does Cosmos DB know which physical partition to store or retrieve a given JSON document? That is our control, under our control, by defining logical partitions, which we do. We, the human, we're still relevant. We pick a partition key when we create a container that defines this dashed blue boundary around documents that all share the same value. And in this example, I'm going to go with /username and use the username property to partition my data, because this will, let's say, be a social networking scenario where if we now forget about the physical partitions, which is usually the best idea, right? We concern ourselves with our logical partitions. Using the username property would mean that each user's documents are self-contained in their own logical partition. Tim's documents are in one, Andrew's documents are in another, etc. And each of these documents here could be documents of different types. This could be Tim's profile. The next several could be Tim's posts. The next several could be Tim's likes. And the next several could be Tim's comments, all of which have different JSON structures. But what they all share in common is the username property Tim, clustering them together in the same logical partition, if you will. Okay. So with that fundamental laid down, let's talk about ordered change events. This is the critical concept when choosing a partition key. Now, I'm talking now about an event-driven scenario, e-commerce, where a user is shopping with their shopping cart. And what we're doing is we are capturing everything that occurs as an event. So everything is an insert. This is an event-driven scenario, so everything is an insert. Even a delete or an update is an insert reflecting that delete or update. So the cart gets created, an item gets added, another item gets added. That first item gets removed. That's actually another insert, simply reflecting the fact that the first item got removed. And of course, then a third item got added and the second item got modified, right? And then the cart got checked out. And now imagine any number of microservices listening in on these events, doing their independent respective jobs, one calculating tax, one managing inventory, one managing fulfillment, one perhaps maintaining a materialized view of the shopping cart that you could look at as a kind of a stateful thing that shows, the current state of the shopping cart at any point in time that then in itself could be queried, right? All of these microservices running independently, listening off the change feed. But one thing's obvious, that it's critical that these events are processed in order. And if we ever need to replay the change feed for a given microservice that has gone rogue, that has had a failure, that for whatever reason it needs to kind of be rewound and replayed, you need to be guaranteed that the events will replay in this sequence, right? Because you can't remove an item obviously before you add it. So everything needs to be in sequence. And how is this achieved with something that as elastically scalable as Cosmos DB? Is by you choosing the right partition key. So in this particular case, I would say that the cart ID is the proper partition key to use, right? Let's say we have two physical partitions under the covers. The fact is, each one of them has their own individual change feed. Yeah, we get to view one change feed logically, like we get to view one container logically, but for each physical partition behind the container, there's actually a change feed as well that is emitting events in the order they occur. So when shopper one starts shopping, that's the first event for that shopper. We create a document. It lands in its own physical partition. A logical partition, which ultimately lands on physical partition one. Another shopper comes along, and now they are, have a logical partition for them that is existing on physical partition two. they are performing events independently of one another, but each time there's an event that occurs, you can see that it is not only emitted, but persisted to the change feed, right? And as we kind of, whoops, I'm a little ahead of myself there. As we kind of look at this picture here now, within any given cart, as indicated by the color coding, the events are in order, right? Because I've chosen the cart ID, A, B, C, D, etc., as the partition key. And they are, even as the carts are interleaved, each individual cart is persisting and therefore would be replaying its events in sequence. Now, at some point, this is going to scale elastically. Cosmos DB will spin up a third physical partition, which of course will have its own change feed, and then roughly half of the partitions, I've only got space on the slide to show one, but it would be roughly half of the logical partitions from the partition being split would move over, and simultaneously those persisted events that from that change feed would then migrate over as well, maintaining their sequence within each cart, even as now more shoppers come along and it continues to scale elastically, right? Because you're a big Amazon.com, right? And so you're just scaling and scaling. And now if you look at each individual change feed and you scan it down and you look at the color coding, you'll see that per cart, all the events are in sequence, even as they're being shuffled around. So again, even though there are 3 physical change feeds, luckily we only have to deal with one. We get multi-threading benefits from the change feed processor library that you'll see a lot more about shortly, that will just simply aggregates and interleaves them. But even so, again, per cart, the events are in sequence. So this is clearly critical to you choosing the right partition key for your event-driven scenario. And this is simply a shopping cart example. And now I'm going to, well, first of all, I want to pause for a moment and make sure that my audio is coming through clear, as well as my screen share.
You're all good, Lenny.
Oh, great. Thank you, Jay. So remember that list: replication, denormalization, etc. We're going to go through all of them. First few just with some slides, and then we'll dig into some really cool demos. Okay. So this is often referred to as analysis paralysis, because when you choose a partition key, you will do so based on your most common querying patterns, which will often fall into like the 80% category or better. And that will satisfy 80% of your queries. That's the partition key to choose. But what if you really have two very separate querying patterns, and this is a very read-heavy scenario? But if both of those are true, then you're not going to be able to determine, you're not going to be able to resolve to the best partition key. And the answer will be to do replication, which means to essentially take the hit of writing an update to a replica, but have each replica of the same data partitioned differently, partitioned according to your usage patterns. So for example, if I have my cart, this is a materialized view of a cart, if you will. It's a stateful representation of a cart. So there are updates here. I'm either doing this as a relational database, or I'm materializing this view from events of a shopping cart, as we just saw. But whatever the case, this document will be updated and potentially deleted, right? Even if it's part of the materialized view. And I'll partition it on the cart ID, which will allow me to really select any cart by ID very efficiently, or filter within a cart. I could filter on quantity, I could filter on product within a cart, and it would all be a very efficient single partition query, because the partition key is known to the query. And so the query is routed directly to the appropriate partition for the data. But if I run this other seemingly innocent query where I need to get all the surface pros across all carts, now that is a cross-partition query, because I'm obviously spanning multiple carts, cart IDs. So those would be cross-partition queries. And if they fell into the 20% or fewer, these are not the queries that typically hammer away at our application. It could be okay for them to be cross-partition queries. But if it's extremely read-heavy, because we are a big Amazon.com after all, and our consumers, our clients, our users, our integration partners are hitting our APIs, what have you, and querying consistently for data by item from carts, well, then we will simply spin up a replica called cart by item, and we will listen on the change feed and maintain a replica. So as items are inserted and updated, we'll have a rep copy. However, the copy will be partitioned on the item property, and our application will route queries where the cart ID is known to the cart container and where the item property is known to the cart by item container, and solve that problem. Let me just do a quick check on time processing. Okay, we're doing good.
Yeah, you got about a good 40 minutes within the.
Yeah, I'm keeping track, so I think we'll be okay.
All good. And we got a ton of questions that we're gonna get to after you finish.
Yeah, questions. I will try to pause right before our actual live demo and handle those, and then jump into our live demo.
Great, sounds good.
Right. So, updates. This is important to kind of realize that interim updates, they're not retained by what's called now the latest version change feed. This is the newest thing now. There's a latest version change feed, and there's a so-called full fidelity change feed. Basically, if you update the same document multiple times, the change feed will only persist the most recent version of that document. Now, for our replication scenario, that is not a problem. If we ever needed to blow away our replica container and rebuild it by replaying the change feed, we would only need the latest version of an update, right? So it's fine, but in other scenarios, that could be a consideration. And the bigger consideration is that deletes, they're not written to the quote unquote latest version change feed at all. Only to the full fidelity change feed, which we'll talk about in a moment, which is brand new. But traditionally, deletes, they're not written to the change feed. And so, an update, if the quantity changes from 3 on the left, our microservice will pick it up and can change it to the 3 on the right. The same thing if it went from a 4 to a 4. But if we actually needed to now delete this document, we couldn't just delete it, because that would not be emitted to the change feed, and it would not therefore be deleted from a replica, and we would wind up with an unwanted, orphaned document on the right, and we don't want. So the solution there is to use the time to live property that we'll see more about in a moment, and that is basically self-expires the document. It's just an ordinary update. So you don't delete the document. You tell Cosmos DB, you update the document by telling it to self-expire in 60 seconds. And much sooner than this. If your microservice is listening, then within a few milliseconds, you'll pick up on it, and you'll see that an update occurred that set the TTL, and you would just go ahead and delete the document from the replica, and then let the document in the cart container self-expire after 60 seconds. It sounds hacky, and that's why. Well, we'll get to that slide in a moment. You'll see that there's been some improvements around that, but they also have limitations. So this all works through the magic of the CFP library. Like, how is it? But before the CFP library, we would have to discover all these physical partitions and each one's change feed, and aggregate it all together, and multi-thread it all ourselves, and manage all the state for checkpoints from the time we last consumed the change feed. All that work we would have had to do, but that is all encapsulated by the CFP library. And that could be a web job, a worker role, right? Really any kind of dedicated capacity on Azure. But the easiest and simplest, which is what I'll show you, is Azure Functions, which essentially wraps the CFP library. If many, if not most of you, or some of you are familiar with Azure Functions and know what they are, but they are very simple, essentially functions. They're triggered, they react to a trigger. And in this case, the trigger that we'll be reacting to is anything being emitted through the change feed. It's generally shared capacity. You can pay for Azure Functions Premium and get dedicated capacity, but it's really the simplest way to get started. And that's what we'll do. So now it's time to talk about normalization. Then I'll pause for questions, and then we'll jump into the IoT demos. So handling relational workloads. Well, Cosmos DB is non-relational. Postgres aside, let's not talk about that right now. But Cosmos DB is essentially non-relational, which means there are no joins and there are no relational constraints, and therefore you need to go about different ways of materializing relationships between your entities than what you might be used to. Where we will denormalize and we will violate the rules of normalization in order to satisfy queries with a single request rather than multiple requests, and achieve that by essentially duplicating data. So here's an example where I've got a customer-facing website. And these are my product documents. And if I have one of these documents in hand, I really don't have everything I need to display this on my web page, because I have a bunch of IDs, but I need to quote unquote join right onto the reference data, onto the metadata to get the category names and the tag names, which are stored, like I said, in the metadata container. That's our master data, where all of the category IDs are defined with their names and perhaps other information, but we really just need their names for display. Well, that means if I want to display all the products in a given category, I have to run not just this query to get all the product documents in the category, but this additional query to get the category name, and worse yet, for each document returned by the first query, this third query with the tag IDs to get the tag names for all the tag IDs. This is very painful. And so the answer, therefore, is to essentially duplicate that data. And what you can see highlighted here is the fact that the category name is present in the product document as well. It's a copy of the master data. Like I said, there might be more master data, but we've calculated that we need the category name to satisfy our most common use case, for which is we need to display the category name. We don't need the other category details. So a copy of the category name in the product document is appropriate. And likewise, a copy of each tag name, in addition to the tag ID, is appropriate in the many-to-many tags array. And so the solution here is denormalization. Because obviously, just backing up, at the point of insert, when I'm inserting a new product, the category name and tag names may be known, and it's easy enough to simply inject that into the document when it's created. But the question then becomes, what if somebody changes the master category name in the relational world? Imagine a left outer join against a table that has reference data, and hundreds of rows would be affected by just changing the category name. How can we achieve the same thing, the same behavior? And that is through denormalization via the change feed. So if I look at this, these are all my products. Yeah, each tag has a name, and each category also has a name. That's a copy, like I said, of the master data. This is the master data for category names and for tag names. And if we have a microservice listening on this product meta container, we can cascade the changes. And I mean literally cascade, where one change on the left would cascade to multiple changes on the right. So if the category name shorts got changed to fun shorts, that would update all of the documents. Or if the singular outdoor tag name got pluralized to outdoors, that would be affected in all the related product documents. Okay, so now is a good time as any to pause, because we're about to move into kind of part 2, section 2 here, which is all about IoT telemetry data. Let me pause for questions.
Sure, we've got a few.
Yeah.
Yeah, so let's try the first one here. We've got it from Timmy the Termite, and wants to know about race conditions. What about race conditions when utilizing this particular architecture?
Well, there's only one instance of the microservice running, and it is multi-threaded and parallelized across partition keys, across physical, one background thread per physical partition. So I don't know that there's necessarily a concern for race conditions. I haven't encountered that. It's something we could look at closer and talk about more later, perhaps.
Sure, sure. Okay. The next question we have is from uh, Fuel Senabel. What if I don't know my querying pattern yet?
Yeah, that's very possible, in fact, right? So very often we can be surprised, and we could even expect these are the most common types of queries our users will run, and then we find out that it's a different type. Yeah, that is one of the pain points of partitioning is that you can't easily change the partition key. There are migration paths that can be taken. Maybe replication is the solution. But if you're simply talking about like I just described on the slides, but if what you're talking about is really where a mistake was made and you chose one partition key and you should have chosen another, there are steps you can take to mitigate the pain associated with migrating that data to a properly partitioned container.
Gotcha. We've got one more question that we'll get to, and then we'll let you continue your presentation. Can you talk about change feed dynamic scaling and how to configure it?
Yes. So you're about to see change feed, running essentially locally through Azure Functions, running locally on my machine. But the question was what about scaling? Did you say?
Yeah, scaling, dynamic scaling.
Right. I this is demo code, so it's a little bit oversimplified. You'll see that we have lock mechanisms in place for thread safety.
Gotcha.
But in fact, if this was a real world production scenario, you would need something more durable that could span CPUs, that could survive, instance reboots. So like something like Redis cache would be more appropriate, but I'm just going to be using a thread safe dictionary in the demos.
Gotcha.
And it will the scale is handled by the CFP.
Sounds good. All right. Well, I'm going to let you continue
Thank
your
you.
presentation, and we'll get to more questions. We've got about 25, 30 minutes.
Yep.
So
This should go. This should be fine.
sounds
Yeah.
good. Well, anybody who's still asking questions, we'll get to the next group of them towards the bottom of the hour. All right. Go ahead, Lynn.
Thanks, Jay. So we had three more scenarios to look at. They were notifications. They were materialized views, and they were data movement. So those three additional microservices we're actually going to see live demos of in the context of this Contoso Airlines IoT scenario. So we're a small airline. We have 12 flights to 6 airports. Plans to expand, but we have the obvious requirements that you would expect for any airline. You need real-time flight info. You need to be able to track your planes. Obviously, you need to be alerted when planes fly where they shouldn't into no-fly zones. You need up-to-date arrival information, and you need some cold storage to permanently archive this data, which is very voluminous, right? Because our planes are, let's say, emitting IoT telemetry at every 10 milliseconds. Right, so the solution is to implement microservices, which is what we're here to talk about, and to generate email alerts when a plane enters an off-fly zone, to generate materialized views, so we get cheap queries for getting up-to-date arrival information and real-time flight information, and we want a microservice that will archive to blob storage for permanent archival. All right, so let's talk about ingesting flight telemetry. I'm going to have a container called a location container. It is going to receive the raw flight telemetry. This is not realistic. In the real world, the flight telemetry would be broadcast and received by IoT Hub, which is a wrapper around Event Hub, which would then send it to Cosmos DB, but very likely along the way pushing it through Stream Analytics, which could potentially aggregate this data. So it's one document per minute or 30 seconds, whatever makes sense, rather than the raw data. But in this demo, we're ingesting the absolute raw data. And that means we need a container that is optimized for write ingestion, not queries. It doesn't have to be optimized for queries. It has to be optimized for ingesting data at a very rapid rate. And we're going to actually achieve that by partitioning on the ID property itself. That's going to give us exactly one document per logical partition. So definitely not optimized for querying because there's nothing's grouped together. But it gives you the maximum uniformity, and when you're bulk loading device telemetry in real time, it is actually the proper choice. So let's jump into a demo, okay? All right, let me start off in the Azure portal. Righty here. You can see I've got this, I know the font's a little small. Let me try to bump that up. Okay. I've got my Contoso Airlines database, and I've got several containers in there. Let's first look at the meta container. It contains just metadata. Like this is actually like not big data, small data. So we have, for example, our list of airports. There's our 6 airports, our list of flights, and this is just metadata. The location container, that's the big one. This is the one that we've been ingesting all this flight telemetry in. Let's look at one item and see how that looks in JSON. Well, there's some static information. Well, first of all, we see an ID property that's a GUID, right? So each document is in its own logical container as we ingest this data very efficiently and rapidly. There's some static information about the flight and its arrival and departure and duration and distance. And then there's all the dynamic information that's changing with each event, the current latitude and longitude, altitude, speed, remaining minutes, remaining miles, arrival time. For demonstration purposes, I added an event called isComplete that is set once and only once when the plane lands. This is an event you don't want to miss. So this is just for demo purposes because very often you don't process each event. You throttle your consumption of the change because it's okay to it's okay not to process every 10 milliseconds. But this is one you don't want to miss no matter what. Notice this time to live. That's a 30-day expiration on this document. So before that expires, well before that expires, I'm going to want this document stored to cold storage, so that we have a permanent archival there. The other 3 containers are all empty. We'll see them in a moment. The arrivals board and current location container are materialized views, and the lease container, I don't know if we'll have time to look at that at the end, but that's where this change feed processor library maintains its state. Like I said, it's empty right now. And let's move on over to this other tab here where I've got a storage account. This is a Azure blob storage account with a container, a blob container, certainly not a Cosmos DB container, just a blob container called flight history, which as you can see is empty at this time. This is going to be our cold storage. My microservice is going to save blob documents here as they self-expire within 30 days on the Cosmos DB side. All right, next thing to show is desktop GUI. This is Windows Forms wrapping WPF Bing Maps control with WPF interoperability. Yes, and it's all possible on .NET 6, believe it or not. So don't let anyone tell you Windows Forms is dead, because it's not. I've consumed the metadata to list my 12 flights and to show pins for my 6 airports. And I can even show a red circle around Washington, D.C. This is our no-fly zone. Planes enter that area, we need to be alerted. All right. Right now I've got an empty arrivals board. Nothing's happening. Our planes are all on the ground. RU consumption is 0. Let's monitor these 2 flights, CA-1001 and CA-1004. These are 2 westbound flights out of JFK, one to LAX, one to Seattle. And again, like I said, nothing is happening. Because I've got these, and here you can see 4 microservices just salivating. They're dormant because our planes are on the ground, but they are listening for events. And as soon as the planes kick off the ground, they're going to wake up. And so let's go ahead and do that. Let me go ahead and open up the generator. Here's the flight telemetry generator, and -C continuous. So as soon as the plane lands, it takes right off again. And they're off. and the microservices are waking up. Yeah, our planes are buzzing along up in the air. Let's Yes, I did, because I couldn't run Outlook before, but you see here, if I could just drag this, there we go. I have, these are brand new emails that just came in. Flight CA1001 has entered in a fly zone. Let's go ahead and look at that.
That sounds dangerous for the
formatted
probably
email. You're receiving this notice
area.
plus flight CA1001. What sounds dangerous?
Going into a no-fly zone.
Well, we've been learning right away. And one unique ability that we have is we have the ability to freeze our planes midair, which I've just done. And they're just frozen in midair, waiting for the command to resume. And let's see how that worked. Jumping on over to the code. You can see that I've got, well, here's my full solution, which is available to you, but we're focused here on these flight telemetry projects. I've got 4 microservices that I'm showing. We're now looking at the email alert microservices. That's the desktop, that's the generator, and there's some shared code. So looking at the first one, if I'm looking at the email alert, one thing I would want to point out is that I can set the port number. So that's how I'm able to run all 4 of these microservices concurrently and debug, I might add, all locally, which is my favorite place, right? Everything works locally. Everything is debugged locally and developed locally and then deployed when you're ready. So this is on port 7071, and I've got the others on 7072, 7073, and 7074. Now looking at the actual, now I should also point out that I could have one project with 4 functions in it, but that would break the kind of isolation that I want to maintain. These are individually built and deployed, right? And obviously, if you combine them into a single project, you're coupling them. So there's only one function in this case. Let's look at the code for the email alert function. I'll get to these private statics in a moment. Let's just focus in on this method decorated with the function name attribute, and that's what makes it an Azure function. Azure function is exposed publicly as email alert, and is in this particular case a Cosmos DB trigger. Listening in on this database, the tooltip says Contours or Airlines. This container, the tooltip says location. This connection string, which is in a configuration file, and this is that lease container that I mentioned, is maintaining state for each of our microservices. And you'll see we only need one lease container, and we can still maintain isolation and isolated checkpoints, if you will, between microservices by giving each one a unique prefix, which by convention I'm naming after the function with a hyphen, because then there's going to be some suffix added. And then all of my microservices will have unique documents in the lease container maintaining state. So one lease container shared by all microservices. In terms of the actual parameters that are passed to your function, it's just these 2, which are the only 2 that you need. It is the documents. They used to pass this to you as an array already. It recently changed to be a string that you can deserialize as you see fit. In this case, I'm just going to deserialize it into a J array and iterate each one and check each one's flight location. In terms of exception handling, we don't have a lot of time to discuss the nitty-gritties here, but you want your microservices to be as lightweight as possible, as minimal as possible, to reduce the amount of errors as possible. And in terms of recovery, the best thing to do, here I'm just logging it to the console, but you should just stash it away. You should not attempt to recover any kind of elaborate recovery procedure in your microservice, because you need to remain responsive to fast flooding events. So the best thing to do is to just stash it away somewhere. So within, I have my typical pattern is to have a for each with a single try catch, and then all the logic is in there. And all we want to do, I said I'll get back to these privates. So we have this spatial private. This is just some business logic that does some no-fly zone um, support, right? Am I in a no-fly zone? That's the 150-mile radius, and it returns you a Boolean. But imagine a database of polygons defining your no-fly zone, right? So we just check to see if you are in the no-fly zone, passing in the latitude and the longitude. I actually have a strongly typed class that matches that location document that we were just looking at, right? And if you're not in a no-fly zone, I bail out, I do nothing, basically allowing the event to fly by, no pun intended, as in, you don't do anything with it because you're not, this microservice is not interested unless you're in a no-fly zone. It's not sending the data downstream, it's not persisting it anywhere, there's no output, there's just what it needs to do. Now, here's what I was talking regarding the earlier question about race conditions and concurrency. This is necessary for the demos to work, but in the real world, you would need something even more robust, like I said, Redis cache. I'm just putting some protection around multi-threaded access to a dictionary between the time you check whether the key exists and the time you determine it's appropriate to add versus update. And I'm throttling. Okay, you'll notice I'm not sending an email every 10 milliseconds, right? That wouldn't be too welcome. We got alerted the moment the plane entered the no-fly zone. And the way this is coded, within a minute later, if the plane is still in the no-fly zone, you will get another email. And the email is triggered by send email down here. This is, again, this is a demo. In reality, you would not want to bloat your microservice with the details of email delivery. You just want to queue this thing for delivery, queue it to a notification, because the more code you have, I don't care how good of a programmer you are, the more code you have, the more potential for an exception to be thrown. There's just no question about it. In here, I'm formatting some nice HTML. We saw what the email looked like. It was nicely formatted because the microservice has been doing all that work and constructing an email and using SendGrid to send it. And that's how that works. But in the real world, you would simply want to queue this for notification and let another integration point consume that queue and manage subscriptions. Maybe it's not just email, it could also be SMS, and all those details don't belong in the microservice, but this is just a demo. Looking at the time, I think we should be done by 10 minutes after the hour, hopefully. It actually picks up a bit of speed here now. Coming back to our flight location map. Sorry. Okay, we just did this, right? We looked at the email alert microservice. So querying real-time flight data, how did we get those cool tracking? How could we track the planes in the air? Well, we're running this top one query against our location container because there's a timestamp property that if you order by descending and you do a top one, you're going to get the latest document, which is the plane's current location. And that makes it possible I didn't show you the tooltips, but I'll show them to you in a moment. As you hover the plane, you get the live updated information. All right, by running this query consistently, constantly. Let's have a quick demo. Let's just monitor one flight, CA 1001. There it is, frozen in midair. And let the planes continue. You see it flying along. There it goes. Maybe a little, I'm going to hover over it. There's the live information achieved by running that query. Let's go over to logs. I'm sorry for I can't increase that font size, but it's showing
I think we lost a little bit of Lenny's audio, but hopefully once this process stops running, it'll come back. So, like I said, we're going to be answering questions at the bottom of the hour. Thank you all. There's so many coming in.
I paused that. I hope my audio is better now.
Now we can hear you.
Are you able to hear? Okay, great. So I paused it, and of course, we're still, as a client, are running this query every 3 seconds, and the cost is 85 RUs. That's just for one flight. If I do all flights, and I'm not monitoring all flights, which are kind of frozen in the air at the moment, but you can see the queries now. I'm running that same query, one per flight, as a single client once every 3 seconds, and look at the RU charges racking up. They are racking up astronomically high. This is not acceptable. This is not sustainable. So the solution is to use a materialized view. I'm going to go back to the location map. I'm going to go back to monitoring just one flight, and I'm going to check use materialized view. And now let's look at the logs. Look at the cost. 1 RU. That's cheap because it can't get cheaper. It's a point read because I'm querying from a materialized view, and I'm querying it once every 3 seconds. The RUs are trickling in. If I increase that to 2 flights, now that's 2 RUs every 3 seconds. 2, 4, 6, right? 3 flights, that's going to be 3 RUs every 3 seconds. So 3, 6, 9, and then 12. Unless you think that 4 is going to be 4 RUs every 3 seconds, you'll see I've switched to using a select statement because that's even cheaper, 3.34 RUs, because I'm querying from a materialized view container that you'll see in a moment that we're maintaining. That is just holding the latest 12 documents for each flight inside of a single logical partition. So it's a tiny container and everything's in a single partition. So it's extremely cheap. Here I'm looking for 4 flights, and I'm getting that real-time flight information, right? All 12? Not 12 RUs because I'm doing 12 point reads. I'm doing 12 flights and it's only costing 4.43 RUs. Again, RU consumption being very, very, very modest as a result of this materialized view. So having a look at that the code for that materialized view. It's the current location microservice. It's similarly throttles. It doesn't update the materialized view every 10 seconds. You'll see some throttling logic in a moment, but it monitors the same database and container. It shares the same lease container with a unique prefix, and all it does is upsert, if you will, updates the current location, right? And there's some should skip logic, which, like I said, throttles it. It only updates the materialized view every 3 seconds. So your materialized view lags behind by 3 seconds, which is acceptable. And at the same time, there's the is complete. You're making sure not to miss the landing. Remember, is complete only set once when the plane lands. You don't want to ever miss that. So you write your microservice never to miss it, but to throttle the rest every 3 seconds. And all I'm doing is maintaining a timestamp so I can throttle every 3 seconds. And all I'm doing with each document is I'm taking that GUID ID, which is useless for querying purposes, changing it to the flight number, and I'm upserting it to a different container, the current location container. I'm going to flip on it back over to the Azure portal and show you there the current location container and the number of items. There's only 12 of them, not 42 million, and they're all in the same logical partitions. So even querying them all together is very efficiently, all 12. Or even if there were several hundred, they would fit comfortably, right? Because these are small documents representing just the latest. You see that the ID was changed to the flight number from the GUID, but otherwise we have the same information. So as I've been here closing, I'm going to say that the arrivals board, it works similarly. So just to review these concepts, we saw how expensive it was to query over that gargantuan container using cross-partition queries. So we build a materialized view, a tiny view with one document per flight. We partitioned on type. We set the ID to the flight number, and then it became extremely cheap. And we had the demo. So I'm a little lagging behind on the slides. Arrival data is the same concept. It's just a little bit more involved, which is to say that, if you could query that gargantuan container to gather the arrival information for an airport of interest. But that would be very expensive again, because you have to group the flights by airport. You have to get them, the most recent documents, which we saw is going to be expensive, and then you have to do the grouping. So you want to create a materialized view that just creates documents like this. You see, this is one for LAX. This is one for Seattle. This is one for Orlando, and each one has an array of flights that are arriving at that airport. And these documents are maintained as the planes are flying by a microservice that is called the arrivals microservice. So I'll show you those documents in the container. They're in the arrivals board container. There, Seattle. Here are the flights arriving in Seattle. Okay, so coming on back to the client. Go to my arrivals board. Let's stop monitoring these flights, and yeah, this is querying that materialized view. What's the cost? 1 RU per airport. Again, very much cheaper than if I was hammering away to construct this kind of grouped view of each airport and what planes are arriving from the raw data. Would have been much more expensive. Here, I picked 4 airports, and I'm paying 4 RUs every 3 seconds by a single client. Extremely cheap, extremely modest. The code also, again, looks very similar. Going on with the arrivals board microservice. So this works a little interesting in that it maintains an in-memory representation of the arrivals board in real time with every 10 millisecond update, but it only upserts the airport's document once every, I think, 5 seconds, is it? So every 5 seconds, this is whether we should skip, and we don't want to, miss the completed flight. But going up to the top level is a similar signature. These are our documents. Could all be multi-threaded automatically for you, and that's why you have to have thread safety around your concurrent accessed data structures. You can see I'm calling update board for every document, but bailing out if you should skip, meaning throttling every 3 seconds. So every 3 seconds, the in-memory board that I'm updating with each document, every 3 seconds that document gets written, and then clients can consume it for displaying the arrivals board. All right. I'm not going to dig into the code that actually maintains that calls update board. It manages those structures. It manages the lists. Within lists, you have a list of airports, and each airport has a list of arriving flights. And it does. Running up on the close, we actually only have one microservice left. Oh, and by the way, again, you can see in properties under launch settings, I'm just setting unique port numbers for each of these to run locally. The other configuration information that's in local settings JSON, obviously, when you deploy your Azure function to Azure, you need to deploy this configuration to Azure because it's going to consume it from there. We'll have it all here in the published inside of that.
Lenny, we're just about short on time. So I wanted to give you a chance to kind of wind down, if you wouldn't mind, just so we can.
Okay. Well, the last microservice that we ran out of time to look at in terms of code was simply writing to this Azure blob storage container, which you recall at the beginning of the session was empty. But if I hit refresh, you can see there are now blob files here And it is using throttling logic as well, so that it once every 30 seconds or once every 60 seconds, it takes a snapshot for permanent cold storage while it self-expires out of Cosmos DB in 30 days based on the TTL. And that is my wrap. Yeah, you can see that was my very last slide was on that data movement for archiving cold storage. And so I want to thank you, Jay, and I want to thank all of you for attending. I hope you found it interesting and informative.
Very, very good stuff, Lenny. Let me go ahead and remove your presentation. You can go ahead, stop sharing it, bring up Cam, and then we'll look at some of our last questions that we might have. All right, there you are. Okay. Let's just get a couple questions in, then we're going to go ahead and finish up. First, we've got from Siegfried. Is there any capability of a change feed that is unique to the change feed feature and could not be done without it?
Pretty much everything I've shown relies on the change feed. It is, the fundamental mechanism for responding to events. So the only kind of alternative there really is kind of something where you want to control the pace. There's also a pull model, which I didn't discuss. We've been looking exclusively at the push model, which is the most common use case where, you want events to be pushed to you. You just sit back and listen. But if you want to control the pace, you can use you can pull from the change feed, but then again, you are relying on the change feed. So in terms of monitoring and replaying events in the order that they occurred, I can think of no other alternative to the change feed for implementing these types of microservices that I've been demonstrating today.
Makes sense. So I'm going to bring Askia back so we can kind of just wrap up, and I'll give him an opportunity to kind of just tell us a little bit more about Reactor and what we can find on it. I've gone ahead and put the Reactor URL on the bottom. Welcome back.
Thank you. Well, yeah, typically we work with external partners, startups, meetup groups, and basically provide a space, we host a space for them either in person to have these meetups, or we can do it virtually as well. So we try to really partner with the community, with the tech community, and the things that we put on don't necessarily have to be Microsoft. We like it if they are, but if they're not, that's not a problem. It's more just about kind of developing the tech community, providing a resource where they can get together and doing what we can in that regard.
Sounds good. Well, do you have any information about a survey or anything that?
Yes, absolutely. Yeah. So I want to just take the time to say thank you to everybody for attending, and thank you to our speakers, Jay and Leonard. And we do have a survey, which the information is here. So if you have any feedback, we'd love to hear what you have to say. So go ahead and fill that out or submit that, and we will definitely take that into consideration. But yeah, that is it for me. So once again, thank you everybody for joining, and thanks for your time.
And we're going to say goodbye to everybody. Lenny, thank you so much for
Pleasure's been mine. Always a pleasure.
I know you've got a lot of events and stuff coming up. I'm going to go ahead and put up your LinkedIn again right there on the bottom of the screen. If you want to get in touch with Lenny, I'm guessing that's the easiest way. Tends to be the easiest way for me. So you can get all the information. Anything you want to close with, Lenny?
Just thanks again for joining, and thanks for hosting, Jay.
You're welcome. Anyway, we'll be back next month. We've got another great session for you. But until then, thanks a lot for being part. Please, if you want to go ahead and do a presentation yourself. I've brought it up a couple times. You can go to our intake form. It is right here at the bottom of the screen. I would love for you to participate. We need our community members to share and tell us about what they're doing and how they're doing it and what you could do using Azure Cosmos DB. So until then, we are so thankful for you, and we will see you next time. Let's give everybody the big wave goodbye. Take care, everybody. Have a great rest of your week.